Hello, everyone! I am absolutely thrilled you're here today. If you're studying Form 1 mathematics, or honestly, if you're just someone looking to finally conquer geometry, you are in exactly the right spot. Today, we're taking on Chapter 13, the Pythagoras' Theorem. Now, I know math chapters can sometimes feel, well, a little bit intimidating, but I promise you, by the time we wrap up this explainer, you're going to see just how incredibly logical and simple all of this really is. Okay, let's dive into this. So before we get buried in the numbers, let's just ease any math anxiety with a really fun piece of history. This famous theorem is named after a Greek mathematician, Pythagoras, because he stated it explicitly. But did you know he wasn't actually the first one to use it? No way. The underlying math was widely known in ancient Babylon and Egypt literally 1,000 years before Pythagoras was even born. So we're not just looking at some abstract textbook rule here. This is a highly practical, ancient tool that humans have been using for thousands of years to build our world. Now, what's really interesting about this slide is that we are breaking this entire chapter into 6 easy, step-by-step pieces to make it super simple to understand. We're going to cover 1. Finding the hypotenuse, 2. The Pythagoras theorem, 3. Calculating unknown sides, 4. The converse theorem, 5. Solving tricky problems, and 6. A quick Chapter 13 summary. Section 1. Finding the hypotenuse. This is the very first step of our journey, learning how to identify the absolute most important side of a triangle. By definition, the hypotenuse is the longest side opposite to the right angle in a right-angled triangle. I really want you to lock in on that key word right there, opposite. The absolute secret trick to always finding the hypotenuse is to first spot that 90-degree corner. You know, that little square symbol inside the triangle, and just look straight across from it. Okay, let's test that out right now. Imagine a right-angled triangle labeled P, S, and Q. The 90-degree angle is sitting right at corner S. Take a second. Which side is directly opposite that 90-degree angle? Have you got it? Yes, it's the side connecting P and Q. Therefore, side PQ is our hypotenuse. Honestly, once you can confidently spot that longest side, you've pretty much won half the battle. Section 2. The Pythagoras' Theorem. Now we transition to the core formula, and I promise, it's just a simple relationship between the sides we literally just learned about. Here is the golden rule. Let's read it carefully together. The square of the hypotenuse is equal to the sum of the squares of the other two sides. Now, I need to throw out a massive warning here. This magic rule only works in right-angled triangles, nowhere else. If it doesn't have a 90-degree corner, Pythagoras' theorem absolutely cannot help you. But when it does have that right angle, this relationship is completely unbreakable. You'll often see the rule written out as a formula. Usually we've got the classic c squared equals a squared plus b squared, where c is our hypotenuse. But sometimes you'll see it written with letters pointing to specific corners, like pr squared equals qr squared plus pq squared. I want you to look at this comparison and really let it sink in that the specific letters absolutely do not matter. Whether you use a, b, and c, or p, q, and r, the relationship stays exactly the same. You take the longest side, square it, and it will perfectly equal the other two shorter sides squared and added together. Section 3. Calculating unknown sides. Let's move to and see how this builds as we apply the formula to find actual missing numbers. Let's look at a concrete example. We've got a triangle where the two shorter sides are 12 and 16, and we need to find the hypotenuse, which is labeled x. Step 1, we set up our equation based on the theorem. X squared equals 12 squared plus 16 squared. Step 2, we just do the math. 12 squared is 144, and 16 squared is 256. Step 3, we add them together to get 400. So x squared is 400. But wait, we don't want x squared, we just want x. So for step 4, we find the square root of 400, which gives us exactly 20. The hypotenuse is 20. See? It's just simple logic, step by step. No blind memorization needed. Now, what if we already know the hypotenuse, but we're missing one of the shorter sides? In this case, the hypotenuse is 26. One side is 24, and the other side is x. Step 1, we write out our formula. 26 squared equals x squared plus 24 squared. Now, step 2 is the trick. To get x squared all by itself, we just rearrange the formula by subtracting. So x squared equals 26 squared minus 24 squared. Step 3, do the math. 676 minus 576 gives us 100.
Finally, step 4, the square root of 100 is 10. So, finding a shorter side simply means subtracting the squares instead of adding them. It's like a giant puzzle.
Section 4, the converse theorem. Now this sounds kind of complicated, but it's really just doing Pythagoras' theorem in reverse to figure out the angles.
Converse simply means running the whole theorem backward. Let's run through exactly how this works. If you square the longest side, c squared, and it perfectly equals the other two sides squared, a squared plus b squared, then boom, you have a right angle. It's a 90-degree triangle. But what if c squared is less than a squared plus b squared? Then the angle opposite side c is an acute angle, meaning it's less than 90 degrees. And if c squared is greater than a squared plus b squared, the angle is obtuse, meaning it's wider than 90 degrees. So by testing the sides, we literally unlock the secret of the angles. Let's put that into practice right now. If you have a triangle with sides measuring 25 centimeters, 24 centimeters, and 7 centimeters, is it a right-angled triangle? Remember the rules we just looked at. We need to find the longest side, square it, and see if it equals the squares of the other two sides added together. Let's do the math. Okay, let's break it down together. Our longest side is 25. 25 squared is 625. Now let's test the other two sides. 24 squared plus 7 squared. That gives us 576 plus 49. When we add those together, we also get 625. Both sides of our equation equal exactly 625. So the crucial point is that because it perfectly satisfies the formula, the answer is an absolute yes. This must be a right-angled triangle. Section 5, solving tricky problems. Now, do not panic. We're just going to look at a multi-step textbook problem that combines everything we've learned so far. Let's walk through this complex multi-step problem together. Imagine a diagram combining a couple of different shapes. Step 1, the problem gives us a triangle with sides 20, 21, and 29. If you test those numbers, 20 squared plus 21 squared perfectly equals 29 squared, so the converse theorem tells us we've just proven that corner is a 90-degree angle. Finding that 90-degree angle is the key that unlocks the rest of the puzzle. Step 2, we use basic angle rules. The angles around a central point always add up to 360. We take 360 minus our new 90-degree angle minus a given 155-degree angle, which leaves us with 115 degrees for the next triangle. Step 3. To find the final missing angle x inside that second triangle, we remember that a triangle's interior angles always total 180. So 180 minus our 115 minus a given 28 leaves us with x equals 37 degrees. By breaking it down step by step, that big, scary diagram just melts away. Section 6, Chapter 13 Summary. Now we transition to our final review, and I just want to say, fantastic job keeping your focus throughout this explainer. You have tackled ancient history, geometry definitions, algebraic formulas, and multi-step logic problems. Consider this your ultimate revision checklist. If you can confidently explain these 4 bullet points, you have absolutely conquered Chapter 13. First, always correctly identify the hypotenuse as the longest side opposite the right angle. Second, memorize the core formula, c squared equals a squared plus b squared. Third, remember the practical rule. Find the hypotenuse by adding the squares, but find a shorter side by subtracting the squares. And fourth, use the converse theorem to check if an angle is right, acute, or obtuse just by testing those sides. You know, math isn't just numbers on a page. The rules we've covered today govern the physical space all around us. And this brilliantly illustrates our final point. Look at the corners of the room you're sitting in, look at the pitch of a roof outside your window, or literally just the diagonal measurement of the screen you're looking at right now. Where else is Pythagoras hiding in your daily life? Keep your eyes open, keep practicing, and thank you so much for learning with me today.